Hey everybody, I'm going to do solving first order linear differential equations, separation of variables. I've never taken this approach before, but it seems like a quick and easy way to do this. Given that y is some function of x, and given that we have an equation containing y prime, and x, our goal is to rewrite the equation in the form g of y times y prime equals h of x, where g of y is some function in terms of y, and h is some function solely in terms of x. Equivalently, we could rewrite it as gy dy dx equals h of x. Again, where g is some function of y and h is some function solely of x. If we can rewrite our equation in this form, then we can separate the variables, so to speak, by multiplying both sides by dx. We multiply this side by dx, and we get g of y times dy dx. But what is dy dx times dx? Isn't that the differential dy? So this just becomes g of y dy. And when we multiply this side by dx, we get h of x dx. Well, let's think. This is a function of x we can integrate. This is an equivalent function of x we can integrate with respect to x. Or by change of variable, we can integrate with respect to y. And we'll just focus on this part of the equation. Once we compute these integrals, this equation will give us y in terms of x. Now, the equation that we get from performing these integrals may give us y implicitly as a function of x, but it will nonetheless give us y as a function of x. Now let's try this with an example, okay? And remember, our goal is to rewrite the equation in the form g of y times dy dx equals some function of x, and then we just multiply both sides by dx. That's what we're going to try to do. Yeah, we're going to start slow. We're going to keep the training wheels on for a minute or two. Let's see if we can get this in the form of some function of y times dy dx equals some function of x. Yeah, I think we can do that. Just divide both sides by y, right? Yep. Here's our g of y. Here's our h of x. And what do we do now? We multiply both sides by dx. And the left side, this dy dx times dx just turns into the differential dy. We have our variables separated. Y's and dy on this side, x's and dx's on this side. So that we just integrate the son of a gun. Integral of 1 over y dy, natural log of absolute value of y. And I'll tell you what, something about our author, whenever it's convenient, he assumes that the variables x and y are positive so that we don't have to use absolute values. And maybe that's not a bad assumption. Oftentimes, the independent variable won't be x, it will be t, and t will be time. And so t will start at time equals 0 and progress forward in positive values. And oftentimes, y will be the physical amount of something present. We can't have a negative amount of something present. So it makes sense that the independent variable t and the dependent variable y would both be non-negative. In this case, we have x and y, but we're going to assume that they're non-negative. Antiderivative of 1 over x is natural log of x. There, we have y given as a function of x implicitly. Can we do better? Can we solve explicitly for y? What do you think? If you're thinking, use both sides as the exponent of e to the x, you're absolutely right. So let's do that. E to the natural log of y is e to the natural log of x plus c. And when we have e to the power of one thing plus another, how can we rewrite that? Can't we rewrite that as e to the power of the first thing times e to the power of the second thing? See, if we were going backwards, e to the power of one thing, e to the power of another thing, the exponents would just add, right? And that's the nice thing about an equation. Even though we're English and we read from left to right, equations can be read from right to left too. So these two things are equal. Now let me ask you something. What do we get if we raise e to the power of a constant? Don't we get another constant? So we'll say e to the natural log of x times c1. And e to the natural log of y, son of a gun, that's just y. E to the natural log of x, that's just x. So we get y equals some constant times x. But there's our solution. But wait a minute. Let me just make sure it works, okay? dy dx, that's just c1. Now, is this equation true? Dy dx equals y over x. Let's see. Y is equal to c1 times x, and x is just, well, x is just x. Dy dx equals c1, oh, son of a gun, it works. Okay. So dy dx does in fact equal y over x, which is c1. So we did indeed find the solution to that differential equation. Well, that was too easy. We got to do another one. Okay, what about this baby? Can we separate the variables? This looks kind of easy. If I just multiply both sides by x, I think that'll do it. Let's see. y prime over y equals x over x cubed plus x. And we can rewrite that as 1 over y dy dx equals 1 over x squared plus x. And then we multiply both sides by dx. And dy dx times the differential dx, that's just dy. So this becomes 1 over y dy is equal to 1 over, x over x cubed plus x. I divide by x. This is a 1. That could have been a costly mistake. Okay. That we have our variables separated, we can integrate both sides. And we're assuming x and y are positive, so I'm going to integrate this and get natural log of y. And over here, see, this is just essentially 1 over a squared plus u squared du, where a equals 1 and u equals x. So this is just going to be arctangent of x, right? Plus some constant. Can I solve for y explicitly? I think I can. Again, just use both sides of the equation as the argument of the exponential function. So I'll have e to the natural log of y equals e to the arctangent of x plus c. I have e to the power of the sum of two things. So that's e to the power of the first times e to the power of the second. And again, e raised to the power of a constant is what? That's right, another constant. We'll call it C1. E to the natural log of y, that's just y, equals C1 times e to the arctangent of x. Now we did have an initial condition, didn't we? Xy equals 1. So let's see what that gets us. Plug in 1 for y. Plug in 1 for x. the arctangent of 1 is the angle whose tangent equals 1. What angle between negative pi over 2 and pi over 2 has a tangent of 1? Pi over 4, right? Oops, 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 oops. Oops, 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 oops. Oh my goodness. Y equals C1e to the arctangent of x. So this is C1e arctangent of 1. Arctangent of 1 equals the angle whose tangent is 1. The angle between negative pi over 2 and pi over 2 whose tangent is 1, that's pi over 4. So arctangent of 1 is pi over 4. And I need to know what C1 is, so I'll divide both sides by e to the power of pi over 4. E to the negative pi over 4 equals C1. Our solution is y equals C1 e to the arctangent x, where C1 equals e to the negative pi over 4. Okay. We're going to put that one to bed before I make even more mistakes. We have some exercises in our text, separation of variables exercises. In our text, do page 37, the A exercises, number 1 and number 2.